In last class, I have discussed about the reinforced earth and how this behavior of reinforced earth beneath the foundation. So, those things I have discussed in the last class. Now, in the last section of the last class, I have discussed over the reinforced retaining wall. Now, today I will discuss how to design a reinforced retaining wall and what is the behavior of this structure. Now, first if I go for that reinforced retaining wall, so, I have discussed that suppose if this is a existing ground, then above that we will construct this reinforced retaining wall. So, we will place one reinforcement here, then we will place another reinforcement here. So, this is will fold there, and then within that two layers, this is the compacted sand, then this is the next layer, this is the next layer, so this is sand. So, this is our reinforced retaining wall. Now, if we consider the failure surface, if it is fails like this, then this is your 45, this angle is 45 degree plus phi by 2. If this is the phi is the friction angle of this compacted field with reinforcement, this filling material. Now, here as I have discussed that the main design components of this type of structure is one is S V is the vertical spacing between the reinforcement. Then next one is the length of the total length of the reinforcement, and then this folding portion, length of this folding portion L0. So, L is the total length of the reinforcement, then S B is the vertical spacing, between the reinforcement, and again the T, this tension, mobilized tension that is developed, that is the material property. So, T is the mobilized tension in the reinforcement. Now, this T cannot be greater than the axial strength of the reinforcement, because otherwise this total info system, that will a possibility that this will fail. Now, the when you are talking about the S B and the length we can see that this is the failure surface of the reinforced earth. Then up to we can divide this L into two parts, one is L R and another is we can divide into L E. So, L is equal to L R plus L E. Now, the question is what is L R and what is L E? L R is the length from the face, suppose this is a face of the reinforcement to the failure surface. So, this much of reinforcement is within this failure zone. So, that is L R, and L E is basically the anchorage length, which is from this failure surface to the end of the reinforcement. Now, this LE is very important. As I have mentioned, then every reinforced structure we should have some, we have to provide some anchorage length beyond this failure surface. The reason why, if I consider or if I consider this reinforced retaining wall, then if this is the failure surface, this inclined line is a failure surface, then what is happening actually, this total soil mass along with the reinforcement is trying to slide along this failure surface, it is failing. Now, somebody has to resist this force, that means, when it is moving downward direction. So, some resistance we have to offer, so that it stand in a stable condition. So, who is giving this resistance? Now, actually, when you are providing sufficient anchorage length of this reinforcement, now this reinforcement anchorage, because of this anchorage length, it is getting some resistance because of the soil and the reinforcement interaction. So, in the when this total system or this soil mass is trying to move downwards, now there is a interaction between the soil and the reinforcement. Because of that, the friction will develop, and when this friction, and because of this friction, there is a bonding between the reinforcement and the soil, and this bonding will allow to hold this total system, as if this total system mass is sliding, and because of this bonding between the soil and the reinforcement, this reinforcement is holding this soil mass, so that it cannot slide. So, now this bonding depends on the how much length we are providing in the reinforcement. If we do not provide a sufficient anchorage length for this type of structure, then what will happen? This total system will slide along this surface. So, now for this purpose, this providing of this sufficient anchorage length is very important. Now, these things we will discuss that how to calculate this provide this sufficient anchorage length, and what are the different expression which is available to get this sufficient anchorage length. So, that means, we have to provide this anchorage length such that there is a sufficient bonding between the soil and the geosynthetic. So, that a tension can develop within the reinforcement, and this because of this bonding total system, this will not slide along this surface, it can hold this surface, this total mass. Now, if I so first we have to decide the what is the SV in the vertical spacing, then this anchorage length, because LR we can easily calculate. If we consider this is 45 minus 5 by 2, so definitely this will be 45 minus this is 5 by 2, this is 45 degree minus 5 by 2, this angle. And if we consider this is the Z is in the downward direction from the top, and if this is H is the height of the reinforced retaining wall. So, then at any depth LR we can easily calculate. Now, the question is how we can calculate the LE. Now, when you are talking about this SV, now as I have mentioned that when this force is developing here. So, that means, because of this bonding or because of this friction between the soil and the reinforcement, as I mentioned in the last class also, that the tension will mobilize. So, tension will develop. Now, and the question is when this lateral earth pressure is acting in this direction, because lateral earth pressure is acting, this is the sigma h at any depth, it is lateral earth pressure is acting from this direction. Now, who is resisting this lateral earth pressure? Here in case of traditional retaining wall, that retaining wall is resisting that lateral earth pressure. Here that lateral earth pressure is counterbalanced by these tension forces. Okay. So, now because this is acting in this from right to left and tension is acting in the opposite direction. So, these two forces will counterbalance each other. So, now if I consider in that way, and if we consider a segment, suppose if I consider a segment between the two reinforcement wall, suppose if I consider this segment. So, between, so if I draw this segment, so this is the segment where reinforcement is here, this is T reinforcement. So, this segment I am drawing here. Now, here at any depth, this is at any depth z from the top. So, this depth is z. So, now the amount of lateral pressure at this point will be K into that sigma h, amount of lateral pressure in this point K into gamma into z, where K A is earth pressure coefficient. Gamma is the unit weight of reinforced soil. Gamma is the unit weight of this reinforced soil and K is the. So, now this sigma h is basically equal to taken by this T tension force. So, if I consider this sigma h and which is acting in this region. So, this is sigma h, the unit of T is kilonewton per meter. Okay. Now, this is the force per unit length, and now here the unit is kilonewton per meter square. So, you have to multiply it with some length. So, that is equal to the S V, because this is S V, because here we have taken this segment from the center of between two reinforcement wall to center of another two reinforcement wall. So, this is S B plus 2 by 2, this is also S B by 2. So, S B by 2 plus S B by 2, this is S B. So, we can write that sigma h into S B, that is equal to T allowable, or that is equal to T allowable. Now, why this is T is the mobilized tension, as I have mentioned that this T modulus cannot be greater than T allowable. So, we provide this is T allowable with some additional factor of safety F s. So, this is F s is the factor of safety. Now, finally, if I write this expression that our T allowable divided by factor of safety, that is equal to sigma h into S B. So, S B is equal to T allowable divided by sigma h into factor of safety. So, that is equal to T allowable divided by K A into gamma z into F s. This F s is generally taken as 1.5. So, now we can write S B is equal to T allowable divided by 1.5 into K A gamma into z. So, we can see that if we keep all the other parameter constant, then T allowable constant, K A constant and gamma constant, then this S B is inversely proportional to z. So, that means at the top required spacing is more compared to the at the bottom, because it is inversely proportional. So, that means S B value is more at the top and it is less at the bottom. So, now if I consider in this concept, so this will give us the, that means if I consider this retaining wall and this is the spacing of different retaining wall, this is the failure surface. So, this will be the L r and this is L e. So, this is S b. So, required spacing here will be very less compared to the top. The next one, to calculate the length, total length. So, total length L is equal to L r plus L e. So, L r we can easily determine. So, this is 45 minus 5 by 2, this is any z. So, L r we can determine in this expression that z h, because this is h, minus z into tan 45 degree minus 5 by 2. So, that any depth, this is z h minus z is this one. So, into tan 45 minus 5 by 2. The next one you have to calculate the L e. So, L r we can calculate by this expression. Now, when you are talking about this mobilized tension is developed, so L e is basically the anchorage length. So, that means this resistance that we are getting is because of this interface action of the soil and the geosynthetic. Now, if I draw a particular soil geosynthetic section, so this is the soil geosynthetic section where T, this is the line, this is L e beyond the failure surface, this is failure surface. This is failure line. So, how this, so L e T is the mobilized tension which is developed, and how this is counterbalanced. So, if T is acting this direction, so there will be a shear stress that will act between the soil and the reinforcement. Now, here the sigma n that is acting here is the normal stress. So, this is acting normal stress and this is tau is the shear stress. So, now we can write that our T allowable, this is also you can consider T allowable, that is equal to tau, that is the shear stress, into L e, and this is acting both the sides. So, into 2. So, tau is the shear stress which is acting opposite to the direction of the T. So, tau into L e, that is tau into L e, that is equal to T allowable, as this is acting both the sides. So, that is into 2. Now, how will get the tau? So, that is 2 into tau is, we can get the tau is expression of the shear strength, that shear strength is C plus sigma n into tan delta into L e, where delta is the angle, interface angle between soil and reinforcement. So, this is the interface angle between the soil and the reinforcement. So, finally, if I go for this expression of this L e, so this is T allowable is equal to 2 into C sigma n tan delta into L e. So, L e expression is T allowable divided by 2 C plus sigma n into tan delta, and sigma n is at any depth the normal stress, that is 2 C plus gamma into Z into tan delta. So, here also we can see And if z is equal to 0 or if z is very small, then LE is more. So, that means the required length of the geosynthetics at the top surface is more as compared to the bottom surface, bottom of the reinforcement. Now, generally in the field soil, the C value, if C value is 0, then we have to consider gamma z into tan delta. Now, here we can say, so that means the most safest design that it is observed from these two expressions, that is the expression 2 and previously sigma v expression, that is the expression 1. So, these are the two main expression, one is to how to determine the sigma v and this is how to determine the LE, anchorage length. See, here we can see that at the bottom of this reinforced wall required spacing is more, and here LE at the top of the reinforcement wall, the required length of the reinforcement is more. So, that means, here if I put the spacing which is required at the bottom of the reinforcement and the length which is required at the top of the reinforced wall. So, bottom of the reinforced wall, that is spacing, and the top of the reinforced wall the required length, then design is safe. But we can see that this spacing requirement is not uniform throughout the depth of the reinforcement. That means, the spacing at the top region required spacing is less compared to the bottom region. So, if I provide the uniform spacing that is required at the bottom, then that is somehow is the wastage. So, that means, we have to design it properly, so that we can make it economical, this design. Similarly, the length which is required at the top region of the reinforcement, if we provide that is throughout the depth, that is also not economical. So, we have to provide the spacing and the length according to that, so that we can make the design more economical. So, now here another consideration, the L0, which is the folding length required, that is basically T allowable into divided by 4 into C plus gamma z into tan delta. So, these are the two lengths required, LE and L0. So, now we will design a reinforced retaining wall. Now, before we go for the design purpose, actually what are the loading condition in the reinforced retaining wall. So, one is our dead load or the load of the reinforced soil itself. So, that is at any j, that is gamma into z into K, that is the dead load. Similarly, if there is a surcharge, so that is surcharge load, that surcharge load is Q into K, that is surcharge load. Then we can go for the live load. So, this is live load. Then this will give us the total load. This is total load. So, these three you can consider, one is the dead load or the load of the reinforced retaining wall itself. This is surcharge load, this is live load. So, these are the lateral pressure we are talking about. This is the lateral pressure due to the dead load, this is the lateral pressure due to surcharge, this is the lateral pressure due to the live load, and this is the combination of these three. So, this is the total lateral pressure which is acting. Now, we will solve one problem and to see how these things are working. So, now this design a reinforced retaining wall with H height of the reinforced wall is 6 meter, gamma of the reinforced soil is 19 kilonewton per meter cube, phi is 36 degree and T allowable is 16 kilonewton per meter. So, we are taking these, and here. So, as I have mentioned that this is existing soil and above that this retaining walls are constructed. So, the properties of these two soil can be different. So, here the phi of the this field is 36 degree, gamma is 19 kilonewton per meter cube, H is given 6 meter and delta is assumed equal to phi. But that can be anything, that can be delta can be 70% of the phi or 80% of the phi. So, here it is taken equal to phi and now k value we can calculate is 0.26. K value we can use this expression 1 minus sin phi divided by 1 plus sin phi. Similarly, the foundation soil it has the properties gamma is 20 kilonewton per meter cube, phi is 15 degree, C is 50 and here for this field soil C is taken as 0. So, C equation is 50 kilonewton per meter square, delta for the foundation soil is taken as 0.95 of phi. So, that is 14.2 degree and C A is taken 80% of the C and that is 40 kilonewton per meter square. So, now these are the properties, this is the properties of the foundation soil and this is the properties of the reinforced soil. Now, we have to design this reinforced earth or reinforced earth foundation. So, now this retaining wall when you consider the if I put this S B expression that is S B equal to T allowable divided by 1.5 into K A into gamma into Z. So, this T allowable is 16, K is 0.26, 1.5 is the factor of safety, gamma is 19 and this is Z. So, this is the so now at different level here the height of the retaining wall is taken 6 meter. So, first as the spacing is not uniform, that is because it is a function of Z, spacing is the function of Z, L E is also a function of Z. Then what we will do? We will take this at different section we will determine the spacing. So, here we are taking at 2 meter, at 4 meter and at 6 meter. 3 different position we will determine the what is the required spacing. So, first if I consider at 2 meter depth, S B is 16.26 into 1.5 into 19 into 2. So, that is 1.08 meter. So, at 2 meter depth S B is 1 point. So, at 4 meter depth S B is 16 into 0.26 into 15 into 19 into 4. So, that is 0.54 meter. Similarly, at 6 meter depth, S B is 0.36 meter. So, we can see at the 6 meter depth 0.36, at 4 meter depth 0.54 and at 2 meter depth 1.08. So, for this case we are taking that I am taking that use S B is equal to 0.5 meter for Z equal to 0 to 4 meter and S B equal to 0.33 meter for Z greater than 4 meter, that means 4 to 6 meter. So, we have to choose this spacing such that, because here required spacing is 0.36. So, we can provide less, we cannot provide more. So, that is 36, we are taking 0.33. Now, it is at 4 meter depth, required spacing is 0.54, we are taking 0.5. Now, you can another question that at the 2 meter we can provide 1. So, that is also possible, that at 2 meter 1 we can provide up to 2 is 1 meter, then 2 to 4 is 0.5, then 2 to 6 is 0.33. So, there will be so many variations. So, to just minimize the variation, I have taken only two types of spacing. So, now here why I have taken 5, because here we have to decide the spacing such that we can place them properly, because here from 2 to 6 meter, if it is required we cannot place point. If I take 0.35, that will be very difficult to place here equal spacing. So, to make it equal spacing and place within this 2 meter, we have taken 0.33. So, the number of reinforcement will be, so that means here at 0.5 meter we will provide 1. So, so this is 1. So, at 1 meter we will provide another 2, 1.5 will provide third number of spacing reinforcement. So, 2 meter, this is the fourth number of reinforcement, then 2.5 fifth number of reinforcement. So, 0.5, 1, 1.5, 2.5, 2.5, then 3, 3.5, 4, then 4.33, 4.67, 5, 5.33, 5.676. Because in the top portion Z equal to 0, we are not providing any spacing, because we will fold this one and we will keep this one open. So, that means the number of reinforcement layer will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, number of reinforcement layer is 14 number. So, that is decided, because this is the XB equation and we have taken. So, here the spacing is greater than 4 to 6 is 0.33 meter and from 0 to 4 is 0.5 meter. So, that means the spacing part is over. Now, here what we can do now, next step is to determine the length. So, first we take that at what depth we have provided the reinforcement. So, the depth that we have provided, that at 0.5 meter depth we have provided the first reinforcement, then at 1 meter depth, that at 1.5 meter, then at 2 meter, then 2.5 meter, then 3 meter, then 3.5 meter, then 4 meter. So, up to 4 it is at the rate of, so up to 4 this is at the rate of 0.5 meter center to center. Now, next one is 4.33, then 4.67, then 5 meter. So, next one is 5.33, then 5.67, then 6 meter. So, total 14 number. Here it is point at the rate of 0.33 meter center to center. So, these are the total 14 number of reinforcement and their corresponding depth. Now, at every depth we have to calculate the length. So, if I consider the first layer length, so that is here z h minus z into tan 45 degree minus 5 by 2, then plus T allowable divided by 2 as C is 0. So, this is gamma into z into tan delta. So, now if I put z equal to 0.5 and every other factors, and here another thing that we should mention, that the minimum anchorage length is 1 meter. So, for this particular factor, that cannot be less than 1 meter. So, L e cannot be less than 1 meter, L 0 also cannot be less than 1 meter. So, that is the condition. So, that means, if by calculating if it is coming 0.8, then you have to provide 1. But if it is calculation by it is coming 2 meter, then you have to provide 2. So, that means, this anchorage length cannot be less than 1 meter. So, 1 meter at least you have to provide L e and L 0. So, now here if we put z equal to 0.5, then ultimately required length at 0.5 meter depth is 3.80 meter. So, by putting this value in this expression, at 0.5 meter depth required L is 3.8 meter. Similarly, at 1 meter required L is 3.55 meter. At 1.5 meter required length is 3.3 meter. By calculation at 2 meter, if I put z equal to 2, then the required length, total length we are talking about, that is 3 meter. So, at 2.5, that is 2.8 meter. So, at 3 meter, that is 2.5 meter. At 3.5 meter, that is 2.3 meter. At 4 meter, that is 2.0 meter. So, at 4.33, that is so these are the calculation that at 0.5 meter, 0.15 meter, 1.5 meter, 2 meter, 2.5, 3 meter, 3.5, 4 meter. So, these are the requirement, and 4.33 it is 1.85 meter, and then finally, at 6 meter the required length is 1 meter. So, now we have to decide which length, because as length is varying from 3.8 meter to 1 meter. So, it is not uniform. So, now as in the during the spacing we have taken the spacing at the rate of 0.5 meter from 0 to 4 meter and 0.33 meter from 4 to 6. Here also at here the maximum spacing requirement up to 4 meter is 3.8. So, in place of 3.8 we have taken that up to 4 meter will provide total length is 4 meter, and here minimum spacing requirement, maximum spacing requirement is 1.85 for 4 to 6. So, that we will provide from 4 to 6 is total length is 2 meter. So, this, but we as we have mentioned that if I take up to 2 meter a different spacing, from 2 to 4 a different 4 to 6, then according to that we have to provide the length. Here up to 2 meter we can provide 4, then from 2 to 4 we can provide 3, then 4 to 6 we can provide 2 meter also, but just to avoid the so many variation we have taken from 0 to. So, that means from 0 to 4 meter L is equal to 4 meter, and from 4 to 6 meter L is equal to 2 meter. So, this is the variation that we are using. So, now as and again from the calculation part we can calculate that L 0 is equal to basically L e by 2. So, now if L e calculation of L 0 is coming out to be 0.1 meter. So, that is less than 1 meter. So, that is the minimum value. So, that is not satisfying the condition. So, L 0 value here we will provide 1 meter. So, L 0 is 1 meter, total length is 4 meter from 0 to 4, and from 4 to 6 total length is 2 meter. So, next one. So, next category is the. So, in the during the design of reinforced retaining wall. So, in the other design of reinforced retaining wall, when you are talking about the cantilever retaining wall or gravity retaining wall, basically we consider the various factor of safety, that means factor of safety for sliding, factor of safety for overturning, factor of safety for bearing, and no tension zone. Here also these things that we have done till now, based this is the spacing and the length, that is the internal stability of the reinforced retaining wall. Now, you have to check for the external stability also. So, those external stability are again similar to the other type of retaining wall, that means you have to check whether this reinforcement will slide or not, because the sliding may take place between the foundation soil and the reinforcement layer. If there is no sufficient bondage between the reinforcement and the foundation soil, so there is a possibility the total reinforced wall may slide along the surface. So, we have to provide sufficient length of the reinforcement, so that there is a proper bondage or between the soil and the reinforcement, so that the sliding can be restricted or sliding can be stopped. The next one is the overturning. So, we have to provide such that this here also weight of the reinforcement is giving the resistance. So, we have to make the reinforcement reinforced retaining wall such that there is no overturning. And another is that the such amount of the soil of the reinforced coming from this reinforced retaining wall, that will give a pressure on the existing soil. Now, if existing soil is very poor, then there is a possibility that there is a very bearing capacity failure of the soil. So, you have to check these 3 again for this reinforced retaining wall. Now, how to check these 3? So, that means here if I consider that this is our total length of the is equal to 6 meter reinforced retaining wall. So, from there up to 0 to 4, 0 to 4. So, suppose this is 4 meter, we have provided the reinforcement whose length is 4 meter, and from here to here, I mean 4 meter to the 6 meter, next 2 meter, we have provided reinforcement length is 2 meter. So, this is 2 meter. Here the spacing is 0.5 meter center to center, here is 0.3 meter center to center. So, this is the reinforced retaining wall. So, that means, this is one is if I consider this is also. So, here up to 2 meter which is spacing of 0.33 center to center, this is up to 4 meter. Now, here the passive this active earth pressure that is acting here, you can consider this is acting as a P active, which is acting at a height of h by 3. So, that is 6 by 3, that is 2 meter from the base. So, now when we consider the sliding and the overturning and bearing capacity failure. Now, first we consider calculate P A. P A is half gamma A square into K A. So, half gamma here we will consider the 19, H is 6 square, K is 0.26. So, this is 88.92 kilonewton per meter. So, if I consider this form, then first we have to consider then weight first to calculate, then when we consider the factor of safety for overturning, that means here this force P A is acting this side, now the weight of the reinforced retaining wall is giving the resistance. So, here we will consider the weight W1 and W2, both are the weight which are acting. Okay, so, this is the W1 and the W2. So, here first we consider the weight of this lower portion. So, that is the weight of this lower portion is 19 into 2 is the width and 2 is the height. So, that is the weight. So, overturning means that is the summation of resisting moment divided by summation of overturning moment or diverging moment. So, here summation of resisting moment, that means this weight into, if I take the moment with respect to this toe. So, that W 2 is acting at a distance of 1 meter from this toe, because this is 2 meter. So, W 2 of the center of this, so 1 meter. So, lever arm is 1. So, weight is 19 into 2 into 2, 19 into 2 is the width and 2 is the height, into the lever arm is 1. For the next one W 1, the total weight is 19 into, this is 4 into 4, and lever arm is half of this 4 is 2 into 2. So, this is the resisting moment, and the overturning moment here is acting here P A, which is 88.92 into, which is act at distance of 2 meter. So, we have to calculate these things, and it should be greater than 3. So, if it is not greater than 3, then we have to redesign it, although it is internal stability wise it is fine, but we have to increase the width of the or length of the reinforcement, so that the weight of the reinforcement can increase. Similarly, the factor of safety for the sliding, again this is the summation of resisting force divided summation of the driving force. So, when you are talking about the sliding, here in this case within the reinforcement interval we have taken C equal to 0, because that was the soil properties, but here C is not equal to 0. So, we have to consider the C when you are talking about the sliding. So, sliding mainly will take place between this layer, the last layer, and the existing, because this is existing foundation soil. So, this is the reinforcement. So, for only this length and the existing soil. So, now the C A addition into 2 is the length here is taken, plus this is W 1 plus W 2, that is the weight into tan delta. Delta of what? Here delta of foundation soil you have to consider. This is not a delta of the field soil, here delta of the foundation soil, because this is the sliding between the soil, foundation soil and the reinforcement. So, this is delta 2 divided by the P A, that should be always greater than 3. If it is not, then you have to increase the length again. So, now here CA is 80% of C, and W1 and W2 we can calculate, this is tan delta into PA. Similarly, for the factor of safety, so this is one factor of safety, this is another factor of safety, and this is another factor of safety, the factor of safety for bearing capacity BC. Now, how to calculate the bearing capacity? That means, the Q ultimate divided by Q acting. So, how to calculate the Q ultimate and Q acting? So, we can consider the last factor of safety, that is bearing capacity, and in Q ultimate by Q acting. So, Q ultimate will be C N C, we can consider, into Q N Q plus 0.5 gamma B N gamma. So, that property you have to consider for the foundation soil. Based on the foundation soil phi, we have to calculate the C N C N Q N gamma, and B width of the foundation will consider the width length of the reinforcement, that is the width of the foundation B, and gamma will consider the gamma of the foundation soil. Here another thing is that here it is mentioned that when you are talking about this is the this will act as a total load of the reinforcement. So, that means, and this is the footing which is resting on the foundation, it is not below the foundation, not at the surface, it is not below the surface. So, that means, here Q value is 0 basically, because when you are talking about this is the foundation, if it is resting with some depth, if it is ground surface, then if it is d f, then we can consider Q equal to d f into gamma, if it is placed at the depth of d f, but if it is placed at the surface, then Q is 0. So, here also it is placed at the surface. So, it can consider that Q value is 0 in this case. So, this is the expression, C will provide the C of the foundation, N C will calculate based on the foundation soil phi, gamma is the foundation soil unit weight, N gamma will calculate based on the foundation phi, and B is the length of the reinforcement. And Q acting, that is basically the weight of the reinforced soil. Here we can consider the weight which is acting, either we can consider 19 into 6, that is the weight that is acting here, and then we put this value, B is the length of the reinforcement, and here this is 19 into 6, then this should be also greater than 3. If it is not, then you have to redesign this section. So, we can see here based on the internal stability, we have to determine the spacing between the reinforcement and the length of the reinforcement, as it is not uniform throughout the depth of the reinforced retaining wall. So, we have to make it more economical. So, that in different depth, different spacing and length we can provide, and then we have to check the external stability, that is sliding, overturning and bearing capacity failure. So, if although the structure is safe within the internal stability consideration, but if it is unsafe based on the external stability, then you have to redesign it, you have to actually you have to increase the length of the reinforcement, you have to design it so that it is satisfy the external stability criteria also. So, this way we can design this reinforced retaining wall, and the next class we will talk about the other foundation on the on improved ground or based on the other improvements. Thank you.